I'm Kota Adachi from Tohoku University. Thank you for giving opportunity to introduce my work here. I want to introduce observational results of environmental dependence of chemical evolution in cosmic new cluster. First, as you know, heavier element amount in interstellar medium is enriched by repeating ejection of synthesized metal and new star formation made from ejected metal. This process, called chemical evolution, is also regulated by inflow from surrounding large-scale structures and gas outflow driven by AGN and supernovae. And these gaseous processes may well depend on the environments, especially at redshift 1 to 3. This redshift range is called by cosmic noon because there is a peak of cosmic star formation rate density in this era. From past simulations, effective inflow from large-scale structures are considered to drive the galaxy formation and at this redshift. And it is considered that there is a transition of a gas accretion mode in cosmic noon. Center figure is hollow mass evolution against redshift. For massive hollow above 10 to 12 stellar mass, there are two regimens of gas accretion mode. In protoclusters in this cold in hot regimen, inflow may be more active because protoclusters are located at nodes of large-scale structures. And as mass growth proceeds, gas accretion rate will become inefficient in this hot regimen due to shock heating. So transition of gas accretion mode thought to be occur in the cosmic noon. But how gas flows actually work on galaxy evolution is still under debate, and it is hard to directly quantify them. To tackle with this problem, we focus on cosmic noon cluster named XCS 2015 at redshift 1.46. This cluster has many spexy confirmed galaxies and gas mass data from past ALMA observation. We conduct atmosphere near-infrared spectroscopy to obtain gas phase meteoricities. And using gas phase meteoricities in our work and gas mass data, we could indirectly estimate gaseous outflow rates by applying chemical evolution models. This is the first result. The left figure shows gas phase matrices derived from the flux ratio of the two emission lines and against stellar mass from SED fitting. And the individual galaxies are shown as red circle points, and square points shows stacked values, including N2 non-detected individual objects. And we found significantly higher meteoricity in cluster galaxies towards field galaxies at similar redshift. The metal enhancement is also seen when comparing the other two clusters at redshift larger than 2, named PKS 1138 and USS 5058. And in right figure, for each clusters, we also derive meteoricity offset from field at each redshift. And our clusters at redshift 1.5 show the larger metallicity offset from field galaxies than other clusters. Uh, we also estimate gaseous outflow rates using chemical evolution models named as gas regulator models, including gaseous inflow, outflow, star formation, and nucleosynthesis. In the figure of metallicity against gas fractions, normalization of tracks mainly depends on a mass loading factor representing outflow strength. And the track with a weaker outflow shows a higher metallicity. And we found galaxies in cluster core shown as orange point is consistent with weaker outflow than field counterparts at similar redshift. We suggest some scenarios explain enhanced metallicity seen in this cluster. First, our target is X-ray detected massive cluster, and results shows higher metallicity and larger offset from field counterparts compared to uh, other clusters at a higher redshift. And actually, the uh, the our target cluster are located in the regime where inefficient gas accretion by shock heating in a hollow mass evolution diagram. So from these results, there may be gas accretion become inefficient due to shock heated intercluster medium, and the galaxies in this cluster tend to lack chance of metallicity dilation by pristine inflow gas. And also, as one of the other possible scenarios, metal enriched outflows are suppressed by dense intergalactic medium in the cluster core, shown in uh, showing in this schematic view. That will lead to fallback of outflow gas and further chemical evolution by recycling the already enriched gas. I will suggest some future prospect with Roman to such galaxy evolution in hazy clusters. First, some studies show metallicity enhancement. Some studies report metallicity enhancement in cluster environment, like our work, but others report metallicity deficient or no trend in cluster galaxies. These controversial results are thought to be due to by difference in evolutionary phase of protoclusters and cosmic variation due to small samples. So we need more large samples of protoclusters in various evolutionary phases.
Koto, you have 2 minutes.
Okay. So Roma WFI enable us to systematic protocluster survey, including both evolved and evolved clusters and younger protoclusters. And one method to detect cluster is photometry using Black feature and 4000 angstrom in rest frame. But the black feature is more prominent in passive galaxies, so there would be bias to passive galaxies in evolved clusters in this method. So to detect these star formation galaxies in younger protoclusters, we can use grism spectroscopy for detection of luminous emission lines. In fact, shown in bottom figure, the sensitivity of the grism is enough to detect O3 emission line from star formation main sequence. And as follow-up spectroscopy to detect gas phase metallicity, we can utilize upcoming instruments. For example, Subaru prime focus spectrograph can observe O3 and H beta to derive gas phase metallicies for galaxies up to redshift 1.5. And moons can also detect lines for up to redshift 2.6 with almost 1,000 fibers simultaneously. And this is a summary of my presentation. Thank you for your attention.
Thank you, Kota. I think we have time for one question. Is there anyone in the audience or online? Okay. So let's thank all of our speakers once more.